Let's look at a pretty classic physics problem. In this problem, I have a spring, which is compressed, and a cart that is right up against it. Now we're going to allow that spring to uncompress in order to push that cart. That cart is going to move along the track and go through a loop-de-loop. And the question I want to ask is, if the spring is compressed 0.4 meters, how fast is the car moving at the top? And that's a pretty classic physics problem. Now, if we use what we know right now, which is basically kinematics and forces, this would be an almost impossible problem to solve. And it would certainly involve a lot of calculus. We're not going to do that today. In fact, we're going to use our new concept of energy in order to solve this problem. And energy is going to, first of all, take the calculus out and make this a really, really easy problem to solve. Now, why is it such an easy problem to solve? Is because energy can be conserved. Conservation of energy means that however many joules of energy you have at the beginning, you must have the same number of joules of energy at the end. Now, it doesn't matter what kind of energy there is. We can have, for example, spring energy because this balloon has been deformed, but then as soon as we let go of the base of the balloon, that balloon goes back to its original shape and we no longer have spring energy. Instead, that balloon starts to move and we have kinetic energy. Now, the total energy that we had was always the same, but how it is expressed can totally change. A very classic example of this is a bowling ball pendulum. So we have a professor, he holds the bowling ball up to his chin, he allows it to swing out and back, and it does not hit him in the chin. Why? Well, it's because in order to hit him in the chin, the bowling ball would have to go higher than where it started, which means that it would have to have more joules of gravitational energy than when it started. And because of conservation of energy, which says whatever number of joules you have at the beginning, you have to have the same number of joules at the end, that means that that bowling ball quite physically cannot end higher than where it started. And so our professor is nice and safe, his chin remains intact. So the same thing is going to happen here. Looks like we're going to have some spring energy at the beginning because of that compressed spring, and then it looks like we're going to have maybe some kinetic and some gravitational energy at the end. But just to make sure and to make it easier on ourselves, we have a bookkeeping system. It's called an LOL diagram. And it's called an LOL diagram because it looks like a giant L, O, and L. Now, each of these three things is going to have a specific purpose. We're going to start with the O in the middle, and this is where we define what it is that we're looking at. So for our problem, we have a cart, we have a spring, we have a track, and we have the Earth. We don't want to forget the Earth. We always want to remember that this is where that's happening. Now this first L is going to be a bar graph, and this bar graph is going to show where the energy is before anything happens. We could have gravitational energy, we could have kinetic energy, we could have spring energy. We're going to ignore dissipated energy as the before. We're only going to count it. We're only going to see how much dissipated energy is accumulated over the course of the interaction. Now the other L is also a bar graph, and it is the after. So where is our energy after everything has happened? It could be gravitational energy, it could be kinetic energy, it could be spring energy, or it could have been dissipated. And that's the beauty of energy. You know, we just have to care about what's happening before anything happens, what's happening after anything happens. I know that the amount of energy in the before and the after has to be the same, and I can totally ignore what happens in between. So we totally get to ignore the spring pushing on the cart, we totally ignore the cart slowing down, everything like that. So before, we do not have anything that is at a high height, so we would say there's no gravitational energy. Nothing is moving yet, so we'd say there's no kinetic energy. But our spring is compressed, so we will add some bars of energy to our spring energy. After, our car is up above the ground, so we would say, oh yes, I have some gravitational energy. Our cart is moving, so we would say, oh yes, we have some kinetic energy. But our spring is no longer compressed or stretched, so the spring no longer holds any energy. And we're just going to go ahead and assume that there's no friction here, just to make our lives a little bit easier. So now we've shown that we've got energy before, right? It looks like I gave it maybe 5 boxes. It doesn't matter how many boxes you do. It's totally up to you. This is just what's called a qualitative tool. Okay, it's only supposed to help you look at it. You don't have to use exact numbers. So we have just spring energy at the beginning, we have gravitational energy, and we have kinetic energy at the end. And if you notice, I have still 5 boxes of energy because I need to show that however much energy I have at the beginning is exactly the same as however much energy I have at the end. So the 5 boxes here must match in the after. Okay? Now this LOL diagram makes it really easy for us to do what's called writing an energy equation. And an energy equation just says whatever kind of energy you have at the beginning has to equal whatever kind of energy you have at the end. So for us, we'd say that spring energy at the beginning has to equal gravitational plus kinetic energy at the end. And this LOL is just a visual representation of that. Okay? If I ever ask you to write an energy equation, this is what I'm asking you to write. I'm asking you to tell me what kind of energy do you have at the beginning and set it equal to whatever kind of energy you have at the end. And it's this energy equation that helps us solve problems. So let's go back to the situation. The spring, whose spring constant is 100 newtons per meter, was compressed 0.4 meters to launch the cart. The radius of the loop is 0.2 meters, and the mass of the cart is 0.5 kilograms. How fast is the cart moving at the top of the loop? So since we've already drawn the LOL diagram and written the energy equation, we'll just start with that energy equation. Spring energy at the beginning, has to equal gravitational plus kinetic energy at the end. Now the equation for spring energy is 1/2 k xf squared minus xi squared. The equation for gravitational energy is 9.8 newtons per kilogram times mass times delta y. And the equation for kinetic energy is 1/2 mv squared. So this is where those equations for all those different energies are going to come into play. I will very rarely ask you to individually calculate an energy for me. It's much more common that you're going to be looking at a situation and have to use conservation of energy to answer a question. And you'll use those individual energy equations within your conservation of energy. So let's try to fill in the numbers that we know. We know that K is 100 newtons per meter. We know that the final stretch is 0.4 meters, so we will square that. And then we'll just assume that 0 is our other stretch. That has to equal 9.8 newtons per kilogram times the mass of the cart, which is 0.5 kilograms, times how high the cart is in the air. And the cart is at the top of the loop. So it's not, I believe that means that it's the diameter. Right, so we could say that our delta y then is 0.4 meters, and then we will add 1/2 times 0.5 kilograms And then we finally get to the one thing that we don't know. Out of all of this stuff, right, out of all of this, all of those variables and values, by the time we actually enter in all the stuff we know, we only have but one unknown, and it is that speed, or that velocity. So if we punch all of this into our calculator, we see that 1/2 times 100 times 0.4 squared minus 0 squared. Well, all of that together ends up being 8 joules. 9.8 times 0.5 times 0.4 is 1.96 joules. And then 1/2 times 0.5 is 0.25. So then we can just do the algebra, right? 6.04 joules equals 0.25 v squared. We divide both sides by 0.25. We take the square root. At the end of the day, we end up getting that the speed of this cart is 4.91 meters per second. And that is so much easier than doing calculus.